Hello, everybody. This week we're going to be talking about ions and ionization. So, the first thing that I want to do is review a little something that we talked about last week. So, last week when we were learning how to write electronic configurations, we introduced this alternate notation where we have a core set of electrons that we're representing as the electronic configuration of one of the noble gases. And then we have the remaining electrons that we write to the right of that. And one of the reasons we said that this was going to be convenient is because these core electrons tend not to participate in any kind of reactions. You're not going to gain or lose electrons from this core set of electrons. What we didn't do is give a name to the remaining set of orbitals where we are going to be losing and gaining electrons from. These electrons here are what are known as the valence shell. So the valence shell is going to be different depending on where we are in the periodic table. For hydrogen and helium, the valence shell is just the 1s orbital. For anything in the p or s block, which I'm going to show you on the periodic table with exactly what I mean by p and s block, but the p and s block together are going to make up the main group elements that we've seen before. And their valence shell are going to be the highest principal quantum number that they have for orbitals, and it's going to be the s and p orbitals in that highest energy level. For the transition metals, which are in the D block, we're going to have both the NS and NP orbitals, but also the N-1D orbitals. And if you remember the Aufbau principle, that's because we're filling these in before we get to the NP orbitals. And then in the F block, or the lanthanides and actinides, or the inner transition metals, as we talked about them before, they're going to have the NS, the N-2F, the N-1D, and the NP orbitals in their valence shell. So these are the orbitals where electrons are going to be added to or removed from in a chemical reaction. Now I want to introduce something you guys may have heard about before if you ever took a high school chemistry class or something, but it's called the octet rule. And this is where the main group elements tend to lose or gain electrons to achieve a filled valence shell. In general, most elements actually want a full valence shell, but the main group ones are always going to. And we call it the octet rule because the main group elements are going to have 8 electrons in their valence shell. They're going to have 2 in a s shell, a s orbital, and 6 in the 3p orbitals. So let's look at an example so that we can see what's going to happen here. So if we look at lithium, we can see it has an atomic mass of 6. Has an atomic number of 3. If we write down its electronic configuration, we can see it has a helium core, and it has this 2s1 valence. So what it's going to do is it wants to get a full valence, and it can do that one of two ways. It can add 7 more electrons to completely fill out this valence shell, in which case it would have a charge of -7, or it could just lose this 1 electron, and then it would just have, it would be isoelectronic with helium, and then it would have a full valence shell in that case. So it's going to do the one that's going to lead to the least amount of charge. So it's going to lose this one, and then it's going to have a positive +1 charge. And you'll note that what's going to happen is when you get a full valence shell, it's going to be isoelectronic, or meaning it has the exact same electron configuration as one of the noble gases. So that's basically what they're all trying to do, and they're trying to do that in a way that minimizes the charge on the element. So now let's talk a little bit about how we're going to write elements so that it's clear that they are ionized. This could be true for just an element or a whole compound with an actual chemical formula. So ionization is noted by adding a charge to the chemical symbol. Charge is calculated as the number of protons minus the number of electrons. So in the case of lithium, we said it's going to lose one electron. So it's going to have one less electron than protons. If I do the math here, I'm going to see that that's a +1. And I'm going to write it just as I normally would, 3, 6, lithium, with this +1 up here at the top. I actually believe in your text, it may actually go with 1 plus up here. Those are pretty much equivalent statements. It depends on which text you're going with how they do it. Or we might forego writing this all together and just write it as lithium +1. Now, what we want to be able to do is we want to be able to predict charges. So we want to be able to predict what the charge is going to be on any given atom. And for the main group elements, it's pretty straightforward. It's very predictable what those charges are. But, and this is where some of the problems can get kind of tricky, transition metals, the lanthanides and the actinides, they tend to have multiple possibilities for their charges. So you could have copper +2, you could have copper +3. Things start to get a little bit more complicated. These different charge states are what they call oxidation states. So if we take a look at our periodic table here, we start to notice this little guy down here, and this is showing us where that S, P, D, and F blocks are. So the S block are these two groups where we're filling in electrons in the S orbitals. This section here, the transition metals, those are our D block where electrons are going to be added into D orbitals. This block over here is going to be our P block. That's going to actually include the noble gases as well. And then down here, the inner transition metals are our F block. So for the main group elements, which I want to remind you are going to be the S and the P block elements, we can really pretty easily predict what the charges are that a element's going to take on according to what group it is. And so if it's in group 1, it's going to take on a +1 charge. Group 2 is going to be +2. We get over here to group 13, we're going to have a +3 charge. We start over here, we have the noble gases. They're not going to ionize, right? They're already really stable. They like their electronic configuration. That's what everybody's trying to get to, is a electronic configuration like one of the noble gases. Here, we're going to take on a -1 charge, -2, -3, and then we get into the middle. Now, we can either lose 4 electrons or we can gain 4 electrons, and they're pretty much going to be about the same, and it's going to kind of depend on which element we're in here with. And in general, they're typically not really going to want to form ionic bonds anyway, so it often doesn't really come up, but it could be a ±4 for this group here. So now that I've brought up the subject of ionic bonding, let's talk a little bit about what that is. So ions do not exist as lone species. Okay, you can't just have a bunch of ions in a container that aren't being counterbalanced. So for every positive ion, we're going to have a negative ion, and they're going to attract to one another, and they're going to form neutral compounds. That's why bulk materials we have aren't charged, right? They don't have electrical properties like that. They would have very different properties if they were allowed to just take on a net positive or negative charge. So for every positive, there's going to be a negative. What's going to happen is the positive and negative are going to attract one another, and these electromagnetic interactions are going to form chemical bonds. And this is one type of chemical bond that can form. We're going to talk about another one in just a little bit here. And ionic bonds tend to form between metals and nonmetals. So if we take a look at our periodic table here again, we're going to remember that this group here and this kind of tan gray here are metalloids. Everything to the right of them, including the actinides and lanthanides, are metals, and everything to the top right of that are going to be our nonmetals. So when one of these guys wants to bind to one of these guys, it's going to form an ionic bond. And do note that this is not actually a guarantee. So it's not a guarantee that they're going to form an ionic bond, but they tend to. Okay, and there's a homework question that's kind of tricky like that. You can't say that they're 100% going to, but in general, they usually do. So let's look at some of the notation that we have here. I actually need to add a 2 here and a 2 here first. So first, let's look at how we're going to write our metal here. So I've chosen sodium. It's going to take on, it's in group 1. It's going to take on a +1 charge. And so it's a positive ion. And we have a word for positive ions. We call them cations. And then over here we have our nonmetal. It is in the halogens. It's going to take on a -1 charge. And this is what we call a anion, okay, because it's a negative ion. I always remember these as silly as it is that this is a cation, so it's cat. Cats are a positive thing. So ions that are positive are cations. You know, it's a little silly, but maybe it'll help you remember. And now I'm going to draw out a chemical reaction. And this is one of our first kind of fully drawn out chemical reactions. So I want to step through it carefully with you guys. First, I'm writing here that I have 2 lone sodium atoms, right? And these are in a solid form. So I put a little bracket here and I put an S in there, and that indicates that this is a solid. To that, I'm going to add diatomic chlorine. So chlorine tends not to be lone atoms. It tends to bind to itself. And I'm going to indicate that by putting a little 2 down here to indicate that this is 2 chlorine atoms that are in a molecule bound to one another. And then I'm going to indicate that that is in the form of a gas, because chlorine's a gas at regular ambient temperatures. Now, I needed to put the 2 here because I have 2 chlorines, and it's going to be 1 to 1, right? So every one of these sodiums is going to bind to every one of these chlorines. So to make sure that I have enough sodium to bind to the chlorines, I have to put the 2 here. And then over here, you can see that we're going to get 2 sodium chloride molecules out of it. That's going to be a solid because this is table salt. We're familiar with that as a solid. And we're going to get 2 of them. And that's because we need mass balance, right? If I start off with 2 sodium atoms, I need to finish off with 2 sodium atoms. If I start off with 2 chlorine atoms, I need to finish with 2 chlorine atoms. And this is a special type of equation where we have the transfer of electrons. It's called a redox equation, where redox stands for reduction and oxidation. Reduction is a term for when something gains an electron. Oxidation is a term for when it loses an electron. So you may have noticed when we wrote that last equation, we didn't draw any ions. And that's because when sodium chloride exists as a solid, there are no free ions in that solution. But what does happen with ionic compounds is that when they're added to water, they dissociate into free ions that are moving around freely inside the water. And the reason for that is that water molecules are basically like little magnets, and they can kind of stabilize these free charges. So we still have just as many positives as we do negatives. So the overall water isn't charged, but there are now free ions moving around. And the way that we're going to write that is we're going to start off with our sodium chloride solid. We're going to draw our arrow, which indicates that we added water. And then we're going to write them as our positive sodium ions and negative chloride ions. And we're going to write AQ next to them. This stands for aqueous, meaning that they are now suspended in water. So this has some implications when it comes to electricity. So in their solid crystalline state, so the sodium chloride solid, ionic compounds do not conduct electricity. But when dissociated, the charged ions can move independently, and then they readily conduct electricity. They like to conduct electricity. So an example would be like water in and of itself is not conductive. Even though we always see water as a conductor, you say like don't let something that's like an electrical appliance or something get wet because you'll get electrocuted. It's not the water that's conducting it. It's the stuff that's inside the water. So if I had pure water, which we never have, even the water in your tap and stuff has a lot of things dissolved in it, and it's not going to conduct electricity, but if I added salt to it, then all of a sudden it can. And I've drawn a little picture down here to kind of indicate how this works, right? So if I had a battery and I attach the positive end down into a solution of salt, and I attach the negative end down into the solution of salt, what's going to happen is the battery is going to push electrons off of its positive end. It's going to come down here. A negative charge is going to build up here. And the positive sodium ions are going to go to that end. Over here, we're going to be drawing electrons away from it. We're going to develop a positive charge at this tip here. And the negative chloride ions are going to go to there. And there's going to be two reactions that start to take place. So what happens is for every electron that goes out here, it's going to combine with one of the sodium ions, and it's going to form sodium metal. It's going to like start to form on the tip here. And then over here, where we have the chloride ions giving up their electrons, they're going to turn into a gas. And they're going to free up an electron. And we didn't actually even write that right. We need our 2 there because we know that that's a diatomic. We're going to form that chloride gas. And then an electron is going to be freed and flow up into there. So the moral of the story is, once dissociated, our ionic compounds will now conduct electricity. Some other properties that are going to be important to keep in mind for the homework is that ionic compounds have high melting points, they have high boiling points, and they have a whole bunch of other properties too. They tend to be very dense materials, they tend to be very brittle, they'll break easily, And they have quite a few other properties, but the important ones that I want you to keep in mind is that they have a high melting point and a high boiling point. Let's go over an example problem now. Our problem is, what ionic compound would form from magnesium and bromine ions? So first, we need to write down what the magnesium ion is going to be. It's going to be a cation. It's in group 2. It's going to have a 2+ charge. And bromine, as one of the halogens, it's going to have a -1 charge. And we need to combine these together, but we need to combine them together in such a way that we get a net 0 charge. So that means that we're going to need 2 of our bromines, because they're -1, to neutralize the 2+ on the magnesium. If we draw out our reaction that we're going to get, we're going to have magnesium 2+ plus 2 bromine 1-, and we're going to form magnesium bromide. And we need to put the little 2 here as a subscript to show that there's 1 magnesium atom and 2 bromines in this compound. So naming is always important in chemistry, because we need to be able to say and to write out in text the name of different chemicals. We can't just put on formulas all the time. And so there's some rules to naming ionic compounds. So naming the main group ionic compounds is pretty straightforward, and that's pretty much all we're going to be asked to do in this homework. Naming the ionic compounds with transition metals, lanthanides, or actinides, that's a little bit more complicated, but we're not going to ask you to do that quite yet. And the reason it's more complicated is because, as we talked before, the transition metals, lanthanides, and actinides, they can have different oxidation states. So the rules for the main group compounds, you give the anion the suffix "ide," and that's pretty much it. So if you have a calcium bound to 2 chlorine atoms, you're going to write that name down as calcium chloride. You may have noticed me calling them chloride anions already. Barium with 2 bromines, that's barium bromide. Potassium chloride. Sodium with oxygen, you're going to call that sodium oxide. Okay, so this is where ions and identifying ions is going to get a little tricky. There are these things called polyatomic ions. So poly meaning many, atoms, and they're forming an ion. So this is an ion that's formed out of more than 1 atom. So some elements will bind together to form highly stable ions, okay, as like a group. These are the polyatomic ions. The polyatomic ions will behave as if they are lone ions. They will not dissociate. So they're not going to, a polyatomic made out of a couple of different atoms, they're not going to dissociate into those individual atoms. And this is probably simply illustrated by an example. So here I have sodium, and this guy together, NO3, is what they call nitrate. So this is sodium nitrate, and it's going to dissociate out into aqueous sodium ions, cations, plus this nitrate polyatomic ion with a -1 charge. So what I was saying is that the nitrate doesn't break down into individual nitrogen and oxygens. It's treated as a single unit. And there's not always a fantastic way that these are written out in the language of chemistry. You really have to recognize the patterns when you have a polyatomic. What makes recognizing these a little bit easier is having a list of them. So this is a list. You're going to be prompted with this as some of your supplementary instruction before you get into Newton of all the polyatomics we're going to be talking about that you're going to be responsible for knowing. You can see what the little pattern is that each one has, what charge it should have, and its name. So if you see something like HCO3 in a molecule, you'll know that that is the polyatomic hydrogen carbonate. It's going to be treated as one little unit, and it's going to have a -1 charge. So let's talk a little bit more about the naming of polyatomics. And this doesn't really make a ton of sense. It's kind of a historical thing. And what they did is you'll notice that a lot of the polyatomics tend to differ from one another based on how many oxygens they have attached to them. This is because oxygen is very reactive, it's ubiquitous, it's in the air everywhere. It really guides a lot of chemistry a lot of the time that we see in the natural world. And what they did is they chose the most common one, the one that they saw the most, and they started to give it the suffix -ate. So here's sulfur with 4 oxygens, and we call that sulfate. Okay. Then they took the one that had 1 less oxygen, and they gave it the suffix -ite. So SO3 is sulfite. 1 fewer, you'd think maybe they just give it a different kind of suffix, but they didn't. They actually added a prefix, hypo, meaning less is what hypo means. So SO2 is hyposulfite. And then again, if you added more oxygens than the most common one, they add a prefix. And per, they keep the suffix -ate. So SO5 is persulfate. Persulfate and other perchlorates and stuff like that, these tend to be really reactive, if not just explosive at a lot of times. Like a lot of fireworks are made with perchlorates. Let's go back and look at some examples here. So here I have sodium, and it's attached to an SO4. We call that, or SO2, we call that sodium hyposulfite. Sodium bound to SO3, sodium sulfite. Sodium bound to SO4, sodium sulfate. And then bound to SO5, sodium persulfate. Now that we know that, if we go back to our list, you can see this pattern start to emerge. So here we have NO3, we have NO2. Remember that they both have the same charge on them. One is nitrate, so the NO3 is the most common one, and it's called nitrate. One less, we have nitrite. As we come down here, I saw another one. So O2 is an oxide, but O3, or I'm sorry, oxygen is oxide, but O2 here is peroxide. I thought there was another example of the per in here. Here we go. So we have chlorate, ClO3, ClO4 is perchlorate. Let's take a look at an example. What ionic compound would be formed from aluminum and sulfate ions? In this case, we're going to have aluminum, that's group 3. It's going to have a 3+ charge. We know that sulfate, if we look it up in our table, has a -2 charge. We have to balance these out. So now we have a +3 and a -2. And before, when we just had like a +1, we could just add as many here as we needed to, or as many here as we needed to get to it. But here, things get a little bit more complicated, right? What we need to do is find the least common multiple between 3 and 2. And I drew out a little table here to give you a sense of what I was talking about. So if we think about it, if we had 1 aluminum, we'd be at +3. If we had 2, we'd be at +6. If we had 3, we'd be at +9. If we had 1 sulfate, we'd be at -2. If we had 3, we'd be at -4. At 3, we're at -6. So we need to find a matching one in here where we can match them up, and we can see that at +6 and -6, we would get our neutral compound. So that means that we need 2 of the aluminums and 3 of the sulfates. To write that down, I'm going to write it out like this, and we're introducing some new notation here. So now I have a molecule. It has 2 aluminums, as indicated by the 2 in the subscript down here. And then I put in these brackets, and the brackets are going to tell me that I'm going to apply the subscript to everything inside the bracket. So this is how I'm going to show, even when I have multiple atoms, that I have 3 sulfates. So to determine if I wanted to ask you how many sulfur atoms I had, what you're going to do is you're going to take this 3 and you're going to multiply it by the 1 that's presumed right here. And you're going to say there's 3 sulfur atoms in this molecule. You would take this 3 and multiply it by this 4 if I asked you how many oxygen atoms there were. So it would be 3 times 4, 12 oxygen atoms altogether in this compound.